Can you see the whiteboard? Let me sort of rub this out.
Yes, sir.
Okay, so as I told your colleagues and your lab mates and classmates that we will sit down and solve problems because there seems to be an inability to solve problems in the class in the exams. So we will straight away start solving problems unless you have questions. I had other subjects to cover, but if and when I get the time, which is very unlikely if I keep solving problems, we will try to cover it. But mostly I wanted to cover cooperativity because that's one thing that I did not touch at all. The Hill's equation, the various methods of multiple binding sites. But let's give it a pass. There are many aspects to enzyme engineering that we cannot do unless we have a thorough grounding of what we are doing and understand what we are doing. So today let us sort of solve a very practical problem again. Suppose you have a column and you have a column and let us say it's a tall column and you have packed it with enzymes. I mean, enzymatic beads, and let us say it's like the problem that I gave you in the lab practical, which was a very simple problem. But let us actually assume that we actually solve it, which means that the protein, the enzyme is stuck on the surface of the beads. So very clearly, you have external mass transfer issues, and you want to understand what this external mass transfer is, what is the diffusivity, etc., etc. Now, how do you do this? So you have feed coming in at the bottom and at some substrate concentration S0, and you have some S out. But let us say that you are doing practical experiments. So you have actually put at various points sample ports you have put sample ports here, and let us assume for the sake of simplicity that there is no mixing. I mean, there is no axial dispersion because that will make the problem horrendously complex and you'll have to solve complex differential equations. So let us say axial dispersion is, I mean, obviously we're trying to solve simple problems here, not absolutely realistic problems. Axial dispersion is negligible. Now, if we have this kind of situation and we put in some substrate, let us put some numbers here. Let us say I put in 100 millimoles of substrate. 100 millimoles per minute or some such thing. I mean, some S0. And what we do is we get here a lower S1, here S2, S3, S4, S5, S5, and so on and so forth, S10 or whatever. And from there, and we also know the amount of enzyme that we have immobilized. So that is K2E0. So we know the Vmax of the enzyme. We know the Vmax. And we also know, well, I don't know what numbers to put in here. Some random number I want to put, but may or may not be right. Let us say 50 millimoles per minute, and let us say we have some Km value. We also know the Km value, and obviously we will not actually solve them. I'm just putting these numbers for convenience sake. Say let us say it is 20 millimolar, some. And now the question is, from this data, this set of data here, can you sort of determine what is the external mass transfer rate which is acting? How will you go about it? Can you give me a suggestion? What does this data represent? Of course, I cannot do other experiments. For example, I cannot change the velocity. There is a certain velocity. So if I know there's a certain velocity, or I know the flow rate and I know the cross section area. Again, started so quickly. Can you still hear me?
Yes, sir.
Yes, sir. We can hear you.
So F by V is velocity. So flow rate is known, area is known, cross section area. When I say area, I obviously mean the area. It is not the area. It is not the superficial velocity. Remember, this F by area is superficial velocity, which is when the tank is empty, right? F by area. But actually, there is a. Epsilon is the packing volume. I think we are in trouble today. So epsilon is the packing volume, and we are obviously we know the velocity in terms of the time required for the liquid to reach from here to here, the liquid to reach from. Sorry, can I? Let me try it once more, and then if it doesn't work, I will have to switch off and restart the computer because there's a problem here. Yeah, so we actually have data points at different heights, and if we know the velocity, what do we really know? We know the substrate concentrations S, and if we know the velocity, what do we know here? We actually know the time. You understand? So what we have here is a data plot of actually substrate concentration profiles versus time, which is the same thing as this S1, and this S1 is actually declining like this. So this is the original substrate concentration, and at zero it's something like this, and these are the substrate concentration plots that I think we are. This computer has started giving too much trouble. We know the substrate concentrations at different time points. By definition, we also know because S is going to P, we also know the product concentrations. Because by measuring them. So from this plot, can you tell me, and from the fact that you know that your enzyme kinetics otherwise has a Vmax of this much and Km of this much, from this plot, can you then determine what is the external mass transfer which is acting on it? What is the value of dA? What is the value of Ke, and etc. etc. What is so because this is the enzyme, remember, and this is your film through which convective mass transfer is operating, so that actually the substrate concentration here is S naught bulk. Remember that this bulk, and here the substrate concentration on the surface of the enzyme is some S star. And please note that this bulk is actually this S1, S2. These are the bulk values. Right? So really, the bulk concentration is also changing along the length of the reactor. But can you now combine your understanding of Michaelis-Menten kinetics and the basic equations of mass transfer, which is Ke? What was the equations? Do you remember your basic equations? S naught minus S was equal to the V, where V is equal to V max. Can I sort of switch off the computer and join again? There's some problem here. Yeah. And just let me sort of, I think, restart this laptop. Can all of you hear me and see the board?
Yes, sir, we can hear you.
Okay, fine. So really the question that I'm asking you is the following. No, this is actually still jammed. It's become worse. Okay, so what is this, man? This has really become a problem. Okay, sorry, yeah. Sorry, I disconnected the board. That's not my mistake. Sorry, give me a minute. I disconnected this to right. Yeah. Okay, but I had disconnected my instrument, so I need to. Come on. Yeah. Oh yeah, it's working. What happened? Why did it turn black? Oops. Where's the black one gone? Magenta pen? There's a magenta pen now. Okay, fine, whatever it is, magenta is fine. So really the question that I'm asking you is that what is the level at which the substrate diffuses from this data? And obviously what you have is a plot like this and you have a plot like this. So now how do you ensure from this information to determine the values of the basic equation, the rate equation that we have here, and the diffusivity constants, the substrate concentration, that the substrate, that is the bulk substrate concentration. This is the substrate concentration at the interface, at the solid liquid interface where the enzyme, this is the interface concentration, which is what the enzyme is actually seeing. And so how do you determine these parameters? So that, and then of course later on, how do you plot this Ke as a function of velocity so that you ensure that this gradient, this delta S is small compared to this V? Because you don't want mass transfer to control the rate of reaction. Is it indeed controlling? Is it controlling at the lower end? Let me ask you a very simple question. Or is it controlling at the higher end? Where do you think mass transfer is a bigger problem? At the lower values, or at the bottom of the reactor, or at the top of the reactor? Or in the middle? Where do you think mass transfer is the bigger problem?
It should be at the bottom of reactor.
You think mass transfer is a bigger problem at the bottom of the reactor? Why do you think so? And let me tell you that it is incorrect, but let us sort of actually use eraser actually. See, this is the profile, and I should not have rubbed out the profile, but you can, it's very obvious. So now what is the rate of reaction? Now what is the rate of reaction with respect to substrate concentrations? This is the V versus S plot. Let us assume that this is a V versus S plot, right? And with respect to time, the substrate concentrations tend to go from here to here, 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 and so on and so forth, right? But this is the bulk substrate concentration, but this is actually lower. This is lower because the S that the enzyme sees is less than the S in the bulk. Now, therefore, for all practical purposes, this substrate concentration is actually this substrate concentration. And this substrate concentration is this substrate concentration. So every time it is shifted to the left hand side, right? Now notice that at this range, at this point, in this range, the shifting of substrate concentration from this value to this value, or from this value to this value, or from this value to this value is not changing in velocity. But shifting the substrate concentration from this to this is actually significantly changing in velocity. So it is at lower substrate concentrations that your impact of external mass transfer is very high, and the lower substrate concentrations are at the top of the reactor, not at the bottom of the reactor. So you understand the argument?
Yes, sir.
Okay, so now let us solve the problem. Let us solve it. And I'm going to remove this drawing and clear the canvas and actually solve it. So first of all, let us say that, and this is the problem, that it is as simple as that. This is your real graph, V versus S, which is for the free enzyme. And what are you going to generate? I am going to generate the graph that I obtain with bound enzyme, and this graph by definition is going to be like this. You realize that when S is very, very high, so when S is very high, large, oh, so it's again started, no advantage gain. So when S is high, S is very high, then it does not really matter if there is a drop. K S naught minus S is equal to V. But see, the V is always equal to V max. V is equal to V max when S is much, much larger than Kn. Now, if both these points are much larger than Kn, then we really are not bothered. So really notice that the V max does not change. Because if S is very high, we will anyway approach Vmax, even if there is a diffusion problem, even if there is a diffusion issue taking place. Suppose S, as I said, was 20 millimolar. Suppose we had substrate concentration as 500 millimolars or some such thing. 500 millimolar. Then even if it drops from 500 to 400 millimolar, because the driving force is 500 is some Ke 500 minus 400 is equal to Vm, and S is 400 upon 20 by 400, which is approximately Vm. So Vm is the same whether it is at 500 or 400. Vm is V is equal to Vm always, because this condition is being fulfilled. So the driving force is not a problem. So you can see that the Vmax is the same, but the Km is different. So this is the bound enzyme. Now, first of all, the first job therefore is to find out this graph, V versus S. Right? Now, how do we find this out? So if I have plots of S versus T, what do? I have these numbers here and I have these numbers here. What do? We write the basic equation as V is equal to V max S upon Km plus S. And this Km now becomes Km apparent, because this here is the maximum velocity, and at half the velocity, which is an approximation of Km, this is your true Km, true, and this is your Km apparent. This Km apparent incorporates the fact that your substrate concentrations that the enzyme is going to see is determined by this expression here. Is this argument clear? Now, please solve this equation. What is the solution to this equation? You have the integral form of this equation, right? What is the integral form of this equation? V is nothing but minus ds by dt is equal to Vmax S upon Km apparent. I'm just put a star here, plus S or dash here. And so what do we have? We have Km dash plus S upon S ds is equal to, with a minus sign of course, minus Vmax dt. Is this all right? And so we can integrate these two terms here. And what do we get? Can you tell me? This is Km by S and this is 1. And this is going to be integrated from time t is equal to 0 to time t is equal to t. And this is going to be integrated from initial substrate concentration S0 to S0 to some S, where S is the concentration at time is equal to t. So these are the S values that you are getting at time t, t1, t2, t3, t4, t5, t6, t7, t8. Right? Are you okay with this?
Yes, sir.
Yeah. So this is, I'm trying to keep it as simple as possible. So I assume that there is not going to be any complaint with working so slowly. So what is the basic equation here? Come on.
Km dash ln s minus s naught plus s minus s naught is used to y minus vmt.
So ln
S minus s naught.
s minus s naught. Actually, it's the other way around, but anyway, upon km or into
Sir,
km.
Km is outside, sir.
Okay.
Yes, sir.
Km
Plus
by s plus
s minus s naught is equals to
is
minus
equal.
vmt.
Absolutely. So that is it, right?
Minus
So
minus
now,
sign, sir.
huh?
Minus sign minus vmt.
Minus.
Yes.
And so we divide by t, and we get km ln s minus s naught s minus s naught upon t.
ln s by s naught.
या s by s naught होना चाहिए, वही मैं सोच रहा हूँ कि आप बार बार क्यों बोल रहे हो s by s naught होना चाहिए. I am just waiting for somebody to correct it. Yeah, now it is correct. Plus s minus s naught is equal to minus p. So, so what do we have here? What do we get? So we plot ln, and I will take the inverse of this, s naught by s by t. Okay, and this is also by t. Yeah, this is also by t here. Versus s naught minus s by t. नहीं क्या हो गया? Okay, so is this okay, or am I doing some mistake? Now let me sort of
Yes, sir.
wait for you. Huh?
Oh, it's okay, sir.
So really, okay, let me give you some data points. Let us choose some data. Let us actually, and I want you two people to answer this. So let us say S naught was at time t is equal to 0. Let us say it was 100 millimolar. 100 millimolar. This is in millimolars. And let us say, and I determine minutes. 1, 2, 3, 4. Let us take just 4 data points. Right? And let us say that I get 80 and I get to hair problem. I get 80, 65, 55 and 50. Now can you plot this for me and tell me what is Km and Vm? How would you do this? Just let me hear you out. भाई कुछ आप लोग वॉलंटियर करेंगे तो अच्छा रहेगा. So either you can see, see you can't get the t is equal to 0 plot, obviously. Please remember that, right? Please remember that this t is equal to 0. This plot will be not possible. So you have to start from 1, 2, 3 and 4 only. Okay. So you have only, because S naught at t is equal to 0 is 100 and S naught is 100. So that makes sense. Okay. 0.0 makes no sense. So what do you think the plot will look like? What exactly are we plotting here? What is the x-axis and how will the plot look like? And what will be the intercept and the slope? What is the x-axis? Either in terms of P, which is, remember P is nothing but S naught minus S. हाँ बोलिए, y axis क्या है, x axis क्या है, बताइए.
Sir, x axis is ln s naught by s.
It is ln S naught by S. Okay. And what is y axis? P.
Yes, sir. P.
That's. Are you sure about this? This is okay? Are you sure that this is the right option?
I think so.
Anybody else?
So both divide by T.
So,
Not by S upon T and P by T.
so the question really is, and that is why I want you to go back now and think about what we did wrong here. Remember our basic equation was, let us write it again so that you know you are clear about where we are. So if you think that this by t versus this by t is the correct plot, think about the equation again. We had v is equal to, or rather ds by dt minus ds by dt is equal to v max s upon km plus s. So we had km by s plus 1 ds is equal to minus Vm dt. Is this okay?
Yes, sir.
And the limits were 0 and t and s naught and s and 0 and t. So what was it? Was it right to do this? देख लीजिए km ln, मैं उल्टा कर दे रहा हूं इसको, s नॉट बाई s कर देता हूं, ठीक है ना, s नॉट बाई s तो विद माइनस साइन प्लस s minus s naught, actually s minus s naught, which is okay, s minus s naught for the time being, or let us keep it as, forget this, let us keep s naught here for our convenience, is equal to minus vmt, which was the plot, right? So now what do you think is the plot looking like? This is P and this is ln s. Is this okay, or should we divide by t, or shall this t does not matter?
T is a variable, so it matters, sir.
So how do we incorporate that? So what do we get here? Let us say, for example, tell me at 80, what do we get? What is the number?
1 second, sir.
Sorry? हाँ बताइए, पहला डेटा पॉइंट बताइए, कम से कम बात के देखे जाएंगे. And what is the slope and what is the intercept? So we divided it by t and we divided this by t and we call this as x. And we call this as y. So what is the slope? And we can remove the minus sign, and what is the intercept? And we can take the minus sign on the other side and invert everything. So I hope you can make out that we have this basic equation also as, come on, this is very simple high school, I mean plus class 12th algebra and integration. So we have km and we can make this as s naught minus s naught ln s naught by s by t plus S naught minus S by T is equal to Vmax. So what is the slope?
Minus Km.
Minus K. So how will this line look like? Is this the line or is this the line? Come on, let us have this very simple question. Which is the correct line?
So the red one.
The red one. And what is the y-axis intercept and what is the x-axis intercept? So this slope is minus K.
Vm would be the y-axis intercept and
Will it be positive here? Vm?
yes sir.
Okay. Okay. So so Vm is the positive y-axis intercept. And what is the x-axis intercept? भाई स्लोप माइनस के एम है ये Vm है तो आप लोगों को पता ही होना चाहिए कि x-axis intercept क्या होगा.
Sir Vm upon Km.
Vm upon Km. So from this we can determine the Km values. So this plot allows you to determine from this graph here the slope and the intercept, and so we can join the points and we can plot data and we can join this. And now notice this advantage. We have the data points, but we know Vm. So when you plot this graph, you do not do a least square fit, sum of a square. You do not do a SS, sum of squares, least sum of squares fit, because you fix this Vm at the desired value Vm which you already know. If you do not know it, then it's a different question. Because Vm is not going to change from your free enzyme data. Really what is changing is Km. So it's a single parameter estimation. So you fix this point and try to draw a line which goes through the best points here. So this point is fixed. Okay. So I'm sure that you would have seen this kind of graphs where you fit y is equal to mx, not y is equal to mx plus c. Because c is fixed already. It is whatever value. So if you can do appropriate transposition, you can actually fit this graph and only optimize m, not c, because c is known to you. For example, in your Excel, sometimes they tell you c is 0. Right? Have you seen this option? Hello? So you're trying to fit a y is equal to mx graph, not y is equal to mx plus c graph. And that is important because c is fixed, not at 0, but at Vmax here. So your intercept is fixed at Vmax, and so you can fix your intercept and optimize only m. Sometimes I have seen people, your colleagues, when I was teaching bioprocess, that they would take the graph and they would find out yield coefficient by plotting amount of biomass formed versus amount of substrate consumed, and they would draw a line which would have an intercept. That makes no sense because it means that biomass is formed and zero substrate is consumed, because that was the best fit line. The best fit line has to pass through the origin, because the model dictates that it has to pass through the origin, because you cannot make biomass without substrate consumption. Similarly, the model here dictates that the Vmax is actually fixed from your basic enzyme calculations. These are small points but important to remember, that your Vmax is fixed, and so you cannot optimize just by finding out some other Vmax which is different from the Vmax already known to you from your free enzymes. Now, once you have done this, what do you do further? Now tell me next steps. So now you have done this. So now you have a Vmax which is the same. Hopefully you have done that, and you have a Km apparent. Let us say Km apparent is equal to 40 millimolar. What was the Km apparent otherwise? What was the Km true? It was 20 millimolar. Now can you tell me how will you proceed further? For example, what is the enthalpy efficiency? What is the efficiency, not enthalpy efficiency? What is the efficiency of the reaction when S is equal to Km. I mean, after all, your reaction is going to go here, and at some point, when it entering substrate is 100 millimolar, somewhere here it will be 20 millimolar, right? And you know that this is S is equal to Km true actually. When what is the efficiency of the reaction? How do you remember your formulas?
Sir, actual rate upon rate without diffusion.
Yeah. So without diffusion and so what is your, you have already found out what is your V apparent, what is your V with reaction, what will be your V actual V actual. What is your V actual? V max S. Now what S is 20 millimolar. 20 upon what is Km? Km is your Km apparent 40 plus what is your S 20. So what is the V actual? 2 by 3 V max. Correct? Is this all right?
Yes, sir.
What would it have been if there was no mass transfer? V would have been equal to V max into 20, because that is what I'm saying, 20 millimolar. 20 upon what the true Km would have been used. The Km would have been Km true, right? So it will be 20 plus 20, which is equal to half V max. So what is the efficiency? Sorry, not 2 by 3, 1 by 3, 1 by 3. So efficiency is 1 by 3 V max upon 2 by 3, sorry, half V max. What is the efficiency therefore equal to?
2 by 3, sir.
So 2 by 3. So notice that your efficiency is 2 by 3, 66%. When it has reached, when the substrate concentration has reached 20 millimolar, your reaction rates have been reduced by 33%, by 1/3, because of the presence of external mass transfer. So now, what is the equation connecting efficiency with kappa and x? Let us do these numbers. What was it? X kappa plus 1. आप लोगों को याद है नहीं, अपॉन kappa plus x, यही था ना? So what is kappa? Kappa is Km by S naught, right? Remember? Kappa was the, oh, you've forgotten or you've not attended. Km by S naught. That was the non-dimensional Km, right? So that this is equal to 1. So kappa equal to 1. So what is x then? So this is the kind of simple experiments that you do to sort of understand. So what is x? So efficiency is 2 by 3 is equal to x. Kappa is 1 plus 1 upon 1 plus x. So what is x equal to? Hello? Yeah, go ahead. Solve this, please. This is a rather simple equation.
Sir, 1 by 2.
Huh? X is equal to half, right?
Yes, sir.
X is equal to half. So what does it mean? What does it mean if x is equal to half? What does it mean for the Damkohler number? Okay, think about it. What has happened to x? So really, let me not find it. Let us now say that what was the situation? Let us now say that what was the situation at a concentration here of the beads here, and let us say this was 40 millimolar. So X is equal to, please keep this in mind, and then we will sort of come back to this. So now what is happening at the beads sitting here, where the substrate concentration has gone down to 40? What is the efficiency? So it is Vmax 40 upon 40 plus 40. So it is equal to half Vmax, right? 40 by 40, 40 plus 40, half upon Vmax into 40 upon 20 plus 40. So this is 2 by 3, right? Am I right? At this condition? All of you, yes, no? Fine. So what is efficiency here?
3 by 4.
So notice that here the loss is only 25%. Here the loss was 33%. So as you tend to go up, your loss due to the presence of external mass transfer becomes more and more. And therefore, all such columns suffer from the basic problem that you want the conversion, final conversion, to be as high as possible. So you have to actually make very tall columns, because as you go up and your substrate concentration declines, your external mass transfer makes your efficiency lower and lower and lower. So your conversion rates go down further and further. So that is the big disadvantage of all immobilized columns suffering from external mass transfer, because your efficiencies are not compromised. So if you don't want to make full conversion, you don't want S to go to close to 0 and P to close to P infinity, which is at infinite time, where S goes to 0 and P goes to some whatever value that which is equal to S, at infinite time. You want this to happen, you will end up getting 0 reaction rates and very, very low efficiencies. So this is it. And what is X? X is 3 by 4 is equal to now X, and now kappa is S naught by Km or Km by S naught? What was it? I think I wrote the other way around, right? S naught by Km. Substrate concentration, it cannot be this, right? So this is not correct. This is equal to S naught by Km. So what is kappa? 2. 2 plus am I doing it right? Or you've forgotten completely? 2 plus 1 divided by 2 plus X. So what is X equal to? Hello? Yeah. What is X?
So 2 by 3.
X is 2 by 3. So you can see that we have a situation where we have slowly changing. So what is happening? I hope you realize what is happening. I hope you, instead of saying this, let me sort of write it like this. What is happening? So what is happening is that this was your actual reaction. Now your actual reaction is not being impacted upon, and this is your real reaction which is happening. Why is this Km fallen from 20 to 40? So notice that at 40, S is equal to 40, your reaction rate is half. The reason it is half is because at 40, at S is equal to 40, the enzyme concentration that this fellow sees is this much. That is why you get a reaction rate at 20. The enzyme works at 20. It gives the V is equal to half of V max at S is equal to 20. But to see this 20, it needs an outside concentration of 40. So when the concentration outside is 40, the concentration here is 20, when the reaction is V is equal to V half. So in a sense that I'm trying to say is that Ke 40 minus 20 is equal to half of V max. You get this argument? Or you can do it for any other set of values. You can do it for this value and this value. Notice that this is a smaller value than this, but then this is Ke into this delta S. So this is your delta S. And notice that this is your delta S here. Right? But you get large delta S. Okay. But then your velocities are much higher also. Because V is almost, like 80% of V max. So Ke into say this is something like 80 and 30. So Ke into some delta S, and this is the delta S at all these points, is equal to the value velocity. So notice that the velocities are higher and therefore the delta S is larger. But also notice that even though the delta S is larger, your drop in velocity is not significant. That is why it is close to Vmax. So you can afford to lose a lot of substrate concentrations and yet not get impacted in terms of velocity. Because notice that even in the real case, the drop in efficiency from here is, this is the, sorry. So the opposite argument is that this is the loss in this is the loss in delta V. Because notice that this substrate concentration, I would have got a velocity of this, but I now get a velocity of this. So this is the loss in efficiency. Even though the loss in substrate concentration is this much. This is the loss in substrate concentration. And so I can afford a high velocity because this Ke into delta S is equal to V. This is the basic equation. So this is becoming large, but V is not losing out because it is saturation, and therefore Ke into delta S is equal to V remains the same. Here notice that delta S is smaller, but the loss in substrate in velocity is this much. And here even smaller values, but loss is even larger. So efficiencies go down as you move this way. Delta S has become large. And from there, you can calculate your Ke, choosing any 2 points whatsoever. So you can actually find out your Damkohler number, which is the most important point, which is the real way we do it in engineering. Is I was trying to sort of intuitively tell it to you graphically, but that is also equally important. But the more formal structure is that, I hope you remember your equations again, 1 minus x upon Damkohler number was equal to x upon K plus kappa plus x, right? Wasn't it? Am I right? So for this value, 1 minus x, पहले वाला क्या निकाला था हम लोगों ने x का वैल्यू? हाफ निकाला था ना?
Yes, sir.
तो ये क्या हो जाएगा? हाफ अपॉन dA is equal to हाफ अपॉन 1 प्लस हाफ. तो dA कितना हो गया? ठीक है ना? सो ये भाई हाफ अपॉन हाफ, हाफ कैंसिल हो गया. नीचे वाला न्यूमरेटर मैच करो तो डिनोमिनेटर मैच करा लो, 1.5 होगा. ठीक है ना? मैं इतना टाइम नहीं वेस्ट करूंगा.
3/2
ठीक है ना?
3/2
हो गया ना? Because this is half and this is half, so this is 3/2, so this has to be 3/2. So dA is 3/2, and dA is nothing but, what is dA? I hope you remember dA.
Yes, sir. V actual upon and no, sir.
So dA is equal to 1 upon K into, when there is the velocity 20. ठीक है ना, मान लो 1 है Vmax, whatever, some Vmax, जो भी हो, मान लो Vmax 1 है, ठीक है ना, तो Vmax K by 20 or whatever is equal to 3 by 2. But K into 20 is the driving force, 42 minus 20, ये था ना, यही वाला था ना केस. K into 20 Vmax is equal to 3 by 2. And so you can find out K in terms of, these variables. So K can be found out. Is this clear?
Yes, sir.
So from your data on columns, you can find out for a particular flow velocity, what is the K. And for different flow velocities, then you can find out the K, which is the convective mass transfer function as a function of velocity. That is what we do, and then we discover when K is not increasing further, and that's industrial job. I don't want to bore you with it. And then different velocities, find out K, what is the convective mass transfer equation, and when it starts saturating, we say we don't want velocities higher than this. And that is how we design our columns. For ensuring that K is high enough, it cannot be made higher. So hopefully it will not be rate controlling, but obviously it will be rate controlling at the lower and at the end of the column. Always there will be a problem. So is this clear?
Yes, sir.
Oh, we have run out of time. Okay, sorry, we have run out of time. So now let us stop here. I think I took too much time. I want you to solve the problem that in the next class, I want you to come and solve it, and we will discuss this, which is the problem of the CSTR. In the CSTR, we are going to measure, remember there is no external mass transfer in CSTR because of the shaking, mixing, and we take out output samples here. And we know the radius, and we know flow rates, and we know dilution rates, and we have some S0 and some S out. And from there, can you find out if you know the radius of the beads and you know the Vmax true and the Km true, can you then find out what is the diffusivity, internal mass transfer components, just like we did it for external mass transfer. Can you find out dE? Is this possible for you people to do this? Or shall we do it? Yes.
We'll try, sir.
हाँ, ये data आप लोग try करिए, and next class Friday we will do this. Thank you.
Yes. Thank you, sir.
Sorry for this irritating business of, okay, anyway. Mobile is a big problem, and this laptop is a problem. Sorry.